A very good afternoon to all my dear students and faculty member attending this lecture on VHDL model of combination circuits. Let me introduce myself first. I am Dr. Balwinder Raj, faculty at NIT Jalandhar. I am working in the domain of microelectronics and VLSI design, and specifically microelectronics, semiconductor devices and their application for digital VLSI design using VHDL, Verilog, etc. Today I have delivered the lecture on VHDL model of combinational circuits. Under this I will start with the introduction to VLSI design flow and VHDL. I will give a overview about what is VHDL and how it is important for the VLSI design. Then brief review about the basic concepts of the VHDL. Then our main focus will be on the combinational circuits design using VHDL, that is adder, multiplexer, encoder, decoder, comparator, and then overview about the VHDL synthesis. Once our design is ready with VHDL code, how we can synthesize that code for the actually application of that circuit for the hardware design and implementation on the FPGA. First of all, introduction about the VLSI design flow. In VLSI design flow, first of all we have specification, design specifications, what is the basic requirement, what we specification have, that is number of the inputs, number of the outputs, then control line, clock, whatever the our requirement is there. Then we have to, based on this our specifications, we have to design our design entities and VHDL, HDL, that is hardware descriptive language or schematic editor based design, and this design entries that basically the main decision block or processing unit, that may be a serial, parallel processing. This is the core of our VLSI design, and here we have to add the VHDL model of our combinational circuits that we will discuss in the detail today. Then functional simulation and logic verification. In the functional simulation, we have to verify our code. For example, we have written the code for the arithmetic circuit. The arithmetic circuit, that may be the basic adder, and the function simulation verify that the basic function of the adder, that is adding two numbers, that is we are getting the sum at the output or not. That is basic functional simulation we have to verify. If that functionality is not correct, then we have to go back again and check our code and again follow the same step. Once our functionality is okay, then we have to go for the further step, that is planning, placement and routing, and that is a process that we do in the synthesis process. And then design routed, if again not correct, then we have to go back, otherwise we have to go for the timing simulation and timing analysis, and finally with the our specifications meet timing requirements, then we have to go for the final fabrication or final FPGA implementation. Now we will start with the introduction to VHDL. In VHDL is a hardware descriptive language firstly developed by the USA defense people and later on that is adopted by the IEEE and made a standard, and that standard is applicable as a programming language, and that is basically a combination of both language and hardware, and in that we allow the designer to define its input output ports, its behavioral response, and this language is different from other type of language like C, Pascal, C++, and in the other type of language those are the serial languages, but VHDL is not a C, means it's not a serial language, it's a parallel language, parallel processing language, and the basic advantage for that is this VHDL having high speed and actual implementation of hardware. We think like a hardware and we implement exactly the same steps. Next, the learning VHDL is a combination of learning new language and combined with the reality that you are creating the digital logic, and few basic sticks that is straightforward, like as we think our hardware should work and say we implement. And VHDL having very high or you can say strong database and need to understand the availability of library. We define the library in the start of our VHDL coding, and even in the other type of language also we define the libraries, so that we can access the database from the stored libraries memories. Now next is the why VHDL is required. We basically the main motive or motivation behind the VHDL is its reconfigurable type of programming. Reconfigurable means once we have written a code, we can use that is again and again with the modifications as per our requirement. That is requirement of specification. For example, if we write a code for 16-bit adder today, and in future if we required a adder of 32-bit or 16/4-bit, we need not to write the full code from the start. We can modify our previous code as per our current requirements, and in that what we have to do, we have to just make the small changes in the code, and that is ready for the further extension. And then there are different type of modelings that we do in the basic, that will be discuss in the next few slides. Next is the documentation and testing using simulation, formal verification, synthesis. This is the main difference in VHDL and other type of language. In other type of language there is no hardware interface, or you cannot convert them exactly the hardware, but here we have synthesized that, transfer our code into the next gate level, and then gate level can be optimized. This part we will again discuss in the detail in the later stage. And the main goal that we have for the VHDL is its a design reliability and design process. And design process avoid the errors, in they have the minimum errors, or there is some auto correction in the design. And there is a checker syntax like other language in same is here also. Then next is the basic concepts about the VHDL, that is here in the digital system we are implementing with the digital, like our combinational circuits, those are digital and they are basically operating with the 0 and 1, and if we have single bit 0 or 1, we have to define with the bit, and if we have a array of bits, then we have to define in our entity as a bit underscore vector. Now that is again the different type of integer number system that I am not going in the detail about those number system, but we have to define the range, that is which range we have to work out. And then floating point numbers, that is specifically required for implementing a floating number. But the thing is, for floating point numbers the resources required for the FPGA implementation is very high. If we have a real number, then implementation is easy as compared to the floating point number. Next is the resolved signal concept. In our hardware, if we have a module with single input and single output, then there is no problem. We can directly transfer the signal from C1 to B1, but the problem arises once we have multiple input to the module. Here we have two inputs, C1 and C2, and only one output, that is B1. This is a basically, if we transfer C1 to BC to B1, then this is a illegal type of operation. Then this type of problem can be resolved with the help of a resolved type of function. And in this resolved type of function, what we have to define in our entity as a standard underscore logic. This is resolve time, means we can have two number of driver and only one, even more number of driven inputs we can have. But if we have a standard underscore u logic, then that means that is unresolved type of function, and if we have this type of declaration in the start of our coding, then our multiple inputs, they are not acceptable. If we have standard underscore logic u logic, mean there may be error message, like this is the representation of at which line error is there, then the signal name that has a multiple drivers, mean multiple inputs are there, but which input will be considered at which time, that is not specified, mean which input have high priority, which input have the lesser priority, that we have to specify, or we have to define the resolved logic. Then the compiler has to encounter a signal driven by more than one process, and these type of problems can be arise. Now the question is, can we use standard underscore logic always? The thing is, if we use standard underscore logic always, mean our problem of this multiple driven can be modified, but at the same time we may have problem that our system VHDL simulator, that may take longer time to simulate, because that is always checking if even if there is only one input, then still our simulator will check the multiple input function, and that will create unnecessary delay, and simulation will be taking the longer time. That is why we have to define in our program, we have u logic, mean one input one output, or we have multiple inputs and one output. Next is the priority of the logic and relational operators. Here for example, if we have A is equal to BC, then if we have this type of instruction, when A is equal to B and C, and is the logic function, and then that will be a incorrect function. If we have when A is equal to B and C, this and is a again logic function and gate, and this is again a incorrect, but the correct function is we have to first make A and B and C in brackets like a AND function, and then we have to apply this equal to B, that is the correct function. For example, another example, if we have y is equal to AB plus CD, here there may be some incorrect functions like transferring this function and B or C this into this, or we may have A and B and then this type of, these all are the incorrect function. Correct function is we have to first make this as a AND operation, then OR, and in the last then we have this C and D as a complete expression, Boolean expression, then we have to transfer to the byte. This is the correct function. These type of the small logic error, if these type of the errors are there, during our code writing and checking check syntax, our check syntax may be correct, but we will not get the functional verification as per our specification or requirement. So we have to be careful when we are writing our logic function in this way. Next is the VHDL process. VHDL process are basically divided into two parts. One is the simulation part, and that is other is the synthesis part. In simulation part, we verify its behavioral check, behavioral function, as I have given an example of simple adder. If we have two number, we are getting at sum at the output or not, that behavior actually that is done or not for all the combinational circuits that we have to verify, and then that may be synthesizable or non-synthesizable. Next is the synthesis process. In the synthesis, what we have to define the components and then wire together and describe the interface of these components, then convert VHDL code into actually gate level netlist. This is the core transformation of the VHDL code to the actual hardware gate level netlist, and that netlist we have to again transfer to the end product FPGA, that we will follow the steps in the last. Now next is the VHDL design styles. In the VHDL design styles, there are basically three type of VHDL modeling, mean same combinational circuit, whatever combination circuit we have, we can design in the 3 different ways. We can design our adder with the data flow type, we can design same adder with structural type, behavioral type. And in the data flow, what we have, what we basically write the Boolean expressions and directly deal with the like a flow of data from one side to the other, that is the modeling for the. But main drawback for the data flow is, if we have to simplify the Boolean expression first, and if we have small Boolean expression, that is okay. But if we have large number of inputs, and then we have to go for the behavioral type of modeling. In behavioral, what we do, we write the truth table for the our adder, and we have to implement the truth table in the VHDL, and then we have to find out simulate and synthesize in. But the main limitation for this is truth table is, if we are having we have to design adder of 8-bit, then the number of input combinations will be very large. If we have to design adder of 32-bit or 64-bit, then you can imagine the size of the truth table, huge size is there. So, to minimize that problem, we have to go for the structural. In structural, what we do, we write the components for small separate modules and combine together with the interconnects, and then we simulate, and the code length is very small in the structural. Next is we come to the our main topic, that is the combinational circuit. And in this, we will first discuss what is the combinational circuits, and then we will go for the how we implement these combinational circuit with the help of the VHDL. Combinational circuit is basically a circuit in which we combine our different gates and for the specific task. And the main characteristics of the combinational circuits are, in combinational circuits, the output depend sorry, output depends on the present input. There is whatever the current level present at the input, output depend upon that only, and there is no memory in the combinational circuits. Mean previous input are not able to store, and whatever the current input is there, that will be implemented for the output. And this is the block diagram for the combinational circuit. If we have a to n inputs, we have a to m our outputs, and these combinational circuits may be your half adder, full adder, multiplexer, decoder, encoder, code converter, comparator. All these are the combinational circuits, and these combinational circuits we have to implement with the help of VHDL. Next is the half adder. In half adder, there are two inputs A and B and two outputs, that is sum and carry, and this is also you can say two single bit number adder. Here the main limitation for the half adder is we cannot add the carry, we have to ignore the carry in the half adder, and this is the truth table for the 2 input half adder, and then the circuit diagram for the half adder, and this is the we have to implement in VHDL. Next is the full adder. In full adder, we overcome the limitation of the half adder, means we have the third input also, that is the carry input, and accordingly we have to generate our sum and carry, and this is the truth table for adding the number A, B and carry in, then sum and carry out, and this is the basic circuit diagram for the full adder. Next is the 4-bit parallel adder. In the 4-bit parallel adder, in the previous single bit adder, but practically we require more number of bits adding parallelly. In this is a 4-bit parallel adder, we have the least significant bit A0, B0 and most significant bit here is B3, A3, B3, and this our C in that we have to made permanently at the 0, and in this way we will get the sum S0 to S3 and carry out here. So, this is the basic combinational circuit for the adder, 4-bit adder, and if we have to go for the 16-bit or 32-bit, we can modify this basic block diagram for the higher end. Next is the hierarchical approach used in designing the full adder. In hierarchical design approach means we have at system level we know what we have to design, mean our specification is we have to design a full adder at the system level. We can break down that system in small modules, means we can design the half adders, there may be modules for AND, XOR, or as we require our in the this circuit diagram of the full adder. We can break these sorry, in the small module. This is also known as a top to bottom level approach, and this is the top to bottom level approach is followed in the VHDL design, but there is bottom up approach also. In the bottom up approach, but we have to start from the device, then from the device that may be NPN, MOSFET, PNP type, or from device we have to go for the circuit design. From the circuit design we have to go for the gate level, from gate level we have to go further for architecture and system level. That is the bottom up approach, but bottom up approach is not followed in the VHDL. That is, for that we require a schematic type of editor like Tanner or Cadence or Synopsys type of tool. So in designing VHDL, we have to VHDL modeling of the full adder. As we discussed previously in the modeling, there are 3 type of modeling. Now our task is how to model adder with all 3 type of this modeling. First we will model our full adder with the help of data flow modeling, then we will design the same adder with the help of behavioral, and then we will go for the structural modeling. First, for the data flow, as we discussed, we need to write the Boolean expressions and then implement these Boolean expressions for sum and carry in the with the help of VHDL. This is the VHDL code for the full adder like the with the help of data flow modeling. Here we have to define library IEEE, use IEEE standard logic, then arithmetic, unsigned number. These are the libraries that we have to define in the start, and that is according to our specification. As arithmetic required, as we are going to design the arithmetic circuits, that is adder, and then IEEE standard, that is the basic standard for the VHDL. Then logic design, we are using the logic gates and or whatever logic gates required for the combinational circuits. Then unsigned number, this may be change unsigned or signed as per the adder or subtractor we are designing. Then we have to write the entity FA. FA is the name of the entity, that is full adder, and in this entity is basically the interface of our internal module with the external inputs, and in this we have to write the ports, that is port A, that is the input, B, that is the input, C, that is the input. These are the input required for the full adder, and then C we have to define as the output, that is carry out, and S, that is our sum out, and then we have to end our FA, that is full adder. And here one thing need to be clarified, full adder name, that is FA adder, in the defining the entity, that should be same in the end also. So next step is to write the architecture behavior of full adder. Mean this is the interface for input and output, and this architecture is the main body of our design. That is, whatever the function, whatever the task we have to perform, we have from our combination circuit we have to write here. In the sum we have the Boolean expression, this carry we have the Boolean expression, this, as we have seen the previous slide. These are these expression directly we are implementing in the data flow, and end behavioral, this is the all about the data flow modeling for full adder with the and so here after writing this code, what we have to do, we have to go for the check syntax. Either our check syntax is okay, and that is the direct icon available in the Xilinx software, and once sorry, once we clicked on the check syntax, we will if there is any problem, any error, then there will be a message display and we have to go at that line to correct that. Then check logic, our logic function is okay or not. Then we can check our logic function in a better way if we break this whole program. It's a small simple example, but if we have a complex example, then we can break the whole program in the small modules and check step by step. So that means basically purpose is we can keep our complex circuit in the small modules and simplify that circuit and then go for the debug. So the simulation of small module will be easy. Next, after simulation of the data flow full adder, we will be getting the waveforms like this, and we can verify our function. If we have 0 0, our sum will be 0. If we have 1 1 inputs, then other sum will be 1. In this way we can verify our function. And then next is the test bench waveform for the our full adder. And in test bench what we have to a number of combinations according to our truth table, and we have to apply that input combination to the design step by step and verify the design with the simulation. Means all the combination we have to apply step by step, then we have to check. Next is the this is will be the circuit generated after the simulation from the with the help of modular sim Xilinx for the VHDL. Next is the VHDL code for full adder using our behavioral modeling. Now same adder that we have implemented with the data flow, now we will implement with the help of behavioral modeling. In behavioral modeling we have to write the truth table, and in this truth table what we have to find, we have to find what are the common outputs available in the this sum and out. Here you can see for this if we have all three inputs high, our sum and carry are both high. Second step is if we have all 0, then our sum and carry will be 0 0 both. Now we have to find out the similar combination where our sum and carry out are similar. Here this is the third step where we have sum is 0 and carry is 1. So for these three functions 1, 2 and 3, our sum will be 0 and carry will be 1, and other combination is this one. For basically we have 4 different combinations in our truth table to implement with the help of VHDL. So no further step during the writing the code, again we have to define our libraries, we have to write our entities as per input outputs. Then main difference in the from the previous code is here. In here our first step, if this one first stage, if our A1 V1 C carry, then S will be 1 and C count out will be 1. Second step, if all are 0, then our sum will be 0, carry will be 0. Else if other condition, that is our sum is 0, means what we are doing, we are exactly implementing our truth table with the help of VHDL steps, coding steps. Now here one main thing to note is, in this we are using one process statement, and this process statement having its main function in the behavioral simulation, because in the process statement whatever the instruction are written, those will be simulating in the sequential form. We are saying our VHDL is a parallel language, but with the condition the instructions under the process will be simulating serially or sequentially. Or if we have a multiple process in one program, then all those processes may be simulate parallelly, and that is known as a concurrent statements. So we have to end this first end this process statement, and then we have to go for the behavioral end. Next, after simulating this behavioral, again we can check our with the help of test bench, that is different combination of input. We have to check our functionality of the adder, then we can convert that to the circuit level of design with the help of our Xilinx tool itself. Next is the VHDL code for full adder using our structural modeling. This is a third type of modeling. Again we are going to design the same adder with the different technique of modeling, that is structural. Here in the previous sorry, in this type of modeling what we are going to do, we will write the function, we will write the components for different modules. Means here we are writing one component for half adder HA,